everyone! In today's video, we're going to go over the KutaSoftware Infinite Algebra 2 free worksheet mutually exclusive events. I'll leave a link in the description below so you know how to access this free worksheet. Now, for our first set of directions, it says to determine if the scenario involves mutually exclusive events. So what exactly does this term mutually exclusive mean? Well, just as a refresher, mutually exclusive means that the events cannot occur at the same time. So there's absolutely no overlap between those events. So let's take a look at this in number 1. It says that a spinner has an equal chance of landing on each of its 8 numbered regions. After spinning, it lands in region 3 or in region 6. Note that between these two regions, there's no overlap. It either lands in region 3 or 6. It cannot ever possibly land in both. Therefore, these two events are mutually exclusive. Let's move on to number 2. Number 2 states that a bag contains 6 yellow jerseys numbered 1 to 6. The bag also contains 4 purple jerseys numbered 1 to 4. You randomly pick a jersey, it is purple, or has a number greater than 5. So thinking about this, is it possible to have any overlap? Is it possible that the jersey is purple and has a number that's greater than 5? No, it's not, because the 4 purple jerseys are only numbered 1 to 4. So a purple jersey is never going to have a number greater than 5. So if we think about this as a Venn diagram, we'll put yellow jerseys over here. So we have yellow 1, yellow 2, yellow 3, yellow 4, yellow 5, and yellow 6. And over here, we have purple 1, purple 2, purple 3, and purple 4. So what I'm going to do is I'm going to circle all the purple jerseys, and then I'm going to circle all the jerseys that have a number greater than 5, which greater than 5 does not include 5, so that's just this one jersey here. Notice that there's no overlap, so these events are mutually exclusive. Now I notice that the answer key for this worksheet says that these events are not mutually exclusive, so let's think of a scenario where the events aren't mutually exclusive. Well, think about it. As opposed to randomly picking a jersey and it's purple or has a number greater than 5, what if as opposed to purple, we made this yellow? Well, if I was to circle all the yellow jerseys, there's all the yellow jerseys, and if I circled all the jerseys that were greater than 5, notice that this is inside. There's overlap, so those would not be mutually exclusive. Let's move on to number 3. Number 3 says, a magazine contains 12 pages. You open to a random page. The page number is 8 or 10. Well, opening up a magazine, it's either 8 or 10. Those aren't going to occur at the same time. So this is also mutually exclusive. Let's move on to number 4. In number 4, it says a box of chocolates contains 6 milk chocolates and 4 dark chocolates. 2 of the milk chocolates and 3 of the dark chocolates have peanuts inside. So if we were to think of this, we have a box of chocolate, 6 milks, where 2 of those have peanuts, and 4 dark chocolates, where 3 out of the 4 have peanuts. So you randomly select and eat a chocolate. It is milk chocolate, or it has no peanuts. Is there any overlap? Can those events happen at the same time? And yes, they can, because think about it. If there's 6 milk chocolates and only 2 of them have peanuts, it's totally possible to grab a milk chocolate that contains no peanuts. So because those events can happen at the same time, these events are not mutually exclusive. Let's move on to the next set of directions where we'll start working with probabilities. So our instructions for this next set state to find the probability. So we're going to look at number 5. It says that a magazine contains 14 pages. You open to a random page, the number is 3 or the number is 7. So first we have to think, are these events mutually exclusive? Yes, they are. It's not possible to open to a 3 and to a 7. So we're going to add those probabilities together. And if you want to think of this as a formula, remember in the last worksheet we worked on together, the probability of A or B, the probability of that union, is going to be equal to the probability of A plus the probability of B minus the intersection, the probability of A and B. But if these are mutually exclusive, what's this number? If they can't occur at the same time, there's no overlap. If they're mutually exclusive, this is 0. So we can simply ignore this part when the events are mutually exclusive. Therefore, we're just going to take the probability that we get a 3 for the page number and the probability that we get a 7. And that's the probability of 3 or 7. So out of 14 pages, getting 3, that's 1/14. And then we're going to add that to getting a 7. Well, that's also 1/14. 1/14 plus 1/14 is 2/14, which we can simplify down to 1/7. And in decimal form, that's approximately 0.143. So remembering this, let's move on to number 6. In number 6, it states that a basket contains 3 apples, 3 peaches, and 4 pears. You randomly select a piece of fruit. It is an apple or a peach. Think about it. These are mutually exclusive as well. You're not going to draw an apple that is also a peach if you're randomly selecting one single piece of fruit. It's either an apple or a peach or potentially a pear, but they're not going to occur at the same time. So these are mutually exclusive. So the probability of A or B, that union, is equal to the probability of A plus the probability of B. So if there's 3 apples out of our total, 3 plus 3 plus 4, which is 10, we have 3/10 of a chance of choosing an apple, plus also 3/10 of a chance of choosing a peach. 3 plus 3 is 6 over 10. Dividing each of these by 2, simplifying down, we get 3/5. And 3/5 is equal to 0.6. Let's move on to number 7. In number 7, it states that you roll a fair 6-sided die. The die shows an even number or a number greater than 3. So we have to think, are these events mutually exclusive? No, not quite, because there is an even number that's greater than 3. There's actually 2 even numbers that's greater than 3, 4 and 6. So how are we going to do this probability? Well, because they're not mutually exclusive, we have to remember that intersection. So the probability of A or B, A union B, equals the probability of A plus the probability of B minus the probability of that intersection, A and B. So let's start with the probability of A. What's the probability that the die shows an even number? Let's consider that event A. Well, on a 6-sided die, there's 3 even numbers, so that's 3/6 of a chance. And what's the probability that the number is greater than 3? Well, that's either a 4, a 5, or a 6. So again, 3 numbers. But now we need to subtract that intersection. What's the probability that it's an even number and it's greater than 3? So out of all of the numbers on our die, 1, 2, 3, 4, 5, 6, circling the ones that are even and greater than 3, that's just 4 and 6. So that's going to be 2 out of 6. That's our overlap. So the probability of A and B is 2/6. Now, we'll just add everything up since we have that common denominator. 3 plus 3 is 6, minus 2 is 4, so we get 4/6, which is equal to 2/3. When we calculate that decimal, it's 0.6 repeating, which will round to 0.667. And that's the probability for number 7. And remember, we had to worry about this intersection because the events were not mutually exclusive, meaning that they were able to occur at the same time. Let's move on to number 8. Number 8 says a box contains 3 red playing cards numbered 1 to 3. The box also contains 5 black playing cards numbered 1 to 5. You randomly pick a playing card. It is black or has an odd number. So can the card be both black and odd? Yes, it can, because those black cards are labeled 1 to 5 and there's odd numbers in that range. So these events are not mutually exclusive, meaning that it has overlap. So how do we solve this? It's going to be the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersection B, because they are not mutually exclusive. That intersection is not 0. So we're going to have to calculate for that. And let's state that our probability of A is going to be the probability that it's black, and our event B is going to be an odd number. So the probability that the card is black, well, how many cards are there total? There's 3 red cards and 5 black cards. So a total of 8 cards, 5 of them black. That's 5/8 of a chance of drawing a black card. What's the probability that it's odd? Well, let's actually write this out. I think it'll be easier to see. For the 3 red playing cards, they're numbered 1, 2, and 3. And for the black playing cards, they're labeled 1, 2, 3, 4, and 5. So what is the chance that we get an odd number? Let's go ahead and circle those. 1, 2, 3, 4, 5 out of the 8 total cards. So now we know that the probability of getting an odd number is 5/8 as well. But we have to subtract out that intersection, because think about it. We circled all of these if we were to just select the probability that it's black, and then we also circled some of these again that were odd. So we got to take away that overlap that we counted twice. So subtracting the intersection, the probability that it's black and odd, that's 1, 2, 3 cards out of the total of 8. So subtracting 3/8. 5/8 plus 5/8 is 10/8. Minus 3/8, that's going to leave us with 7/8, which is equal to 0.875. If you're ready, let's move on to our next set of directions. Now, before we jump into this next set of directions, if you're finding this video helpful, please go ahead and click the thumbs up button, or if you have any questions at this point, leave a comment down below. But for now, continuing on, our next set of directions say to determine if events A and B are mutually exclusive or not. And we're going to be utilizing that same formula that we've been working with already. So, number 9 says the probability of A, the probability of B, and we also have the probability of A or B. Remember, if they're mutually exclusive, then that intersection will be 0. So the probability of A or B, we know that it equals the probability of A plus the probability of B minus that intersection A and B. If they're mutually exclusive, this should be 0, which means the probability of A plus the probability of B equals the probability of A union B, or A or B. I just write it as union because that's synonymous. So let's see if this is true. Does 4/5, that probability of A or B, equal 3/10 plus 1/2? Is this true? Let's see. We need to find some common denominator, and I know that 2 goes into 10, so I'm going to multiply this second fraction by 5/5. That's going to give me 3/10 plus 5/10, which equals 3 plus 5 is 8. That's 8/10. Does 8/10 equals 4/5? Yeah, if we were to divide by 2, 8/10 does indeed equal 4/5. So because the probability of A plus B equals 4/5, we know that that intersection is indeed 0. Therefore, these events are mutually exclusive. Let's move on to number 10. In number 10, we have the probability of A, probability of B, and again, they give us the probability of A or B. If they're mutually exclusive, then the probability of A or B is going to be equal to the probability of A plus the probability of B. So we're going to see if this is true. Does 283 over 400, does that equal probability of A, which is 7/20, plus probability of B, which is 11/20? Let's check it out. 7 plus 11 is 18/20. 18/20 does not equal 283 400ths. And think about it. Both of these are even over here, and one of these is odd over here, so that's never going to simplify down. to 18/20. Therefore, these events are not mutually exclusive. There is some overlap that occurred between the two. Let's move on to number 11. And number 11 actually is pretty easy because look, they say that the probability of A and B is equal to some number, and that number is not 0. Therefore, right away, because there's intersection, these events are not mutually exclusive. Let's move on to number 12. Number 12, just as easy as number 11. All we have to do is look at this intersection. The probability of A and B is indeed 0. So because it's 0, these events are mutually exclusive. Let's move on to number 13. Now for number 13, they mix things up a bit by giving us this conditional probability. The probability of A given B equals 33 out of 50. So think about our formula. The probability of A given B, it's a conditional probability. That's the probability of A and B, that intersection, over the probability of B. If these events were mutually exclusive, what would the probability of A given B be equal to? Well, if they're mutually exclusive, that intersection equals 0, so this should be equal to 0, and it doesn't, so these events are not mutually exclusive. Moving to 14, again they give us a conditional, and look, that conditional is equal to 0. And we know for the probability of A given B, that's equal to the probability of the intersection of those two events over the probability of B. And because the probability of A given B equals 0, that intersection had to be equal to 0. These events are indeed mutually exclusive. Let's move on to another set of directions. For number 15 and 16, it states that both events A and B are indeed mutually exclusive. So we just have to find the missing probability. So we know for a fact they're mutually exclusive. If they're mutually exclusive, that means the probability of A and B, that intersection, is indeed equal to 0. So if we're trying to figure out the probability of A or B, we know the probability of A or B, that union, equals the probability of A plus the probability of B minus the intersection of A and B, that probability. We know this is 0 because they're mutually exclusive. So all we have to do is sum up A and B's probabilities. So that's going to be 1/4 plus 13/20. And that's going to be what the probability of A union B is equivalent to, A or B. Finding a common denominator, I'll multiply this fraction by 5/5. So that's going to give me 5/20 plus 13/20. 5 plus 13 is 18, so I get 18/20, which both are even and divisible by 2. Simplifying this down, this is going to give me 9/10. So 9/10 is my solution for number 15. Moving on to number 16, well, it's telling us to find the probability of A and B. I don't even care about this over here because if they're mutually exclusive, we know that the probability of A and B is equal to what? It's equal to 0. So 0 is our solution for number 16. And finally, our last set of directions, find the missing probability. This is similar to up above, except we don't know if they're mutually exclusive or not, so we cannot assume. For number 17, it says the probability of A is 7/20, the probability of B is 7/20, the probability of A or B is equal to 49/80. We have to find the probability of A and B. We know a formula that relates all of these together. The probability of A or B, A union B, equals the probability of A plus the probability of B minus the probability of A and B. Now, because we're solving for this, I'm going to go ahead and rewrite this formula in terms of that intersection. So think about it. If I subtract this intersection over here, but then subtract this and move it over here, I'll have the probability of A and B isolated. So I'm going to have the probability of A intersection B, A and B, equals the probability of A plus the probability of B minus the probability of A union B. All I did here was I moved this to the other side and then moved this to the other side. So now I can plug in and solve. The probability of A is 7/20, the probability of B is also 7/20, and we know that union is 49/80. 7/20 plus 7/20 is 14/20, so I'm going to write that the probability of A and B is equal to 14/20 minus 49/80. Now in order to subtract fractions, I need a common denominator. So I'll have to multiply 20 4 times to get to 80, so I'm also going to multiply 14 4 times. 14 times 4 is going to be 56, so that's 56/80 minus 49/80. What is this equal to? 56 minus 49 is going to be equal to 7, so that's 7/80. The intersection is 7/80. So, given that we do indeed have an intersection that's not equal to 0, we know that these events are not mutually exclusive. Let's move on to the last problem, number 18. In number 18, it gives us the probability of A or B, and A and B, but it does not give us this probability of not B. That's what we're solving for. And in order to solve for that, we need to solve for the probability of B. Because remember, the probability of not B is equal to 1 minus the probability of B. So let's solve for that probability of B first in order to solve for the probability of not B. And just to reiterate, we know these events aren't mutually exclusive because there is indeed an intersection. But continuing on, the probability of A union B equals the probability of A plus the probability of B minus that intersection A and B. Let's go ahead and fill some stuff in. We know the probability of A or B is 283 out of 400. We know that the probability of A is 11/20. We don't know this probability of B, so I'll leave that as my unknown. And we know the probability of A and B is 77 out of 400. So let's subtract or add to the other side to isolate the probability of B. I'll start by adding the 77/400 since I have a common denominator. So adding 77/400 to the other side, 283 plus 77, well, that's going to be 360. So I'm going to have 360 out of 400 equal to 11/20 plus the probability of B. And again, that was after I added 77 over 400 to both sides. Now I'm going to subtract 11/20. But before I do that, I can simplify this down now. Notice that both end in 0, so I can divide each by 10, and both are also even, so I can divide each by 2. So I have 18/20 as opposed to 360/400. And if I'm subtracting this 11/20, that's equal to the probability of B. 18 minus 11, got that common denominator, that's going to be 7/20. So if the probability of B equals 7/20, well, the probability of not B is going to be equal to 1 minus 7/20, which we can think of this one, if necessary, as 20 over 20. 20 minus 7 is 13, so 13/20 is our solution for the probability of not B. And with that, we wrap up this free KutaSoftware website worksheet. If you have any questions, please let me know in the comments below. And as always, don't forget to like, subscribe, and share.